recording. And welcome everybody to our today's seminar. It is my great pleasure to introduce our speaker today, Thomas Pock from the Graz University of Technology. So Tom Pock received his PhD from TU Graz and was on a postdoc research position at the University of Bonn. 2013, he received the most important Austrian prize for young scientists, the START prize, and 1 year later, the ERC starting grant. 2014, Thomas Pock became professor of computer science at the Graz University of Technology, and he's currently leading the Vision Learning and Optimization group. Tom Pock is has a wide research profile working on image processing, inverse problems, optimization, machine learning, and this is a great opportunity to mention that the famous Jean-Paul-Pock algorithm for solving complexly structured optimization problems, which I would say was his greatest contribution to science and to our field. Tom, you have 45-50 minutes for a talk.
Thank you very much for this nice introduction. Welcome everybody to my presentation. I'm talking about learning, so machine learning with energy-based models. So when you look to the recent literature, you can see actually there's a renewed interest in energy-based models. So variational methods or optimization-based methods have been used for decades to produce different models in computer vision, in machine learning, but now there's a renewed interest. For example, I checked that just yesterday there was a CVPR 2021 tutorial on the theory and application of energy-based generated models. So how are energy-based models defined? So let X and Y be a pair of output and input variables. So we say that Y is our input, could be a noisy image when we want to perform image denoising, or it could be a set of stereo images or a video. And in case of stereo, then the output, for example, is the disparity image. And the task of an energy-based models is to infer X from Y. So to infer a stereo image from a stereo pair, to infer a denoised image from a noisy image, to infer a MRI reconstruction from case-based measurements, and so on. And this is basically defined as an energy minimization or optimization approach. So we have an energy E that depends on X and Y. So Y is the input and X is the output. And you try to find that X that minimizes the energy. And this is actually your inference task. So this is your proposal for a solution of your problem. And what is the energy doing? It assigns a certain energy value to the configuration X and Y. For example, if X is close to Y, the energy could be small, or if X has some regularity properties, then the energy should be small, and so on. Of course, depending on how the energy looked like, it could be discrete, it could be continuous, it could be convex, it could be non-convex, smooth, non-smooth, etc. Different algorithms can be used to solve the minimization problem. If the problem is convex, then we are happy, then we know that we can find an optimal solution. If the energy is non-convex, then we must be happy even if we find a stationary point. As Mark just mentioned, the world is non-convex, so this is the problem we have to deal with. The main properties of energy-based models are quite interesting. So first of all, energies can be handcrafted based on first principles. So you can set up a least squares error term. You can think about different regularizers such as the total variation. Mostly those handcrafted energies are physics inspired. But energies can also be learned from data using supervised, self-supervised, or unsupervised learning. And this is actually the main topic of my talk today. A nice feature of energies, I mean, it's nice in terms of a feature, but not nice in terms of minimization, is that they also allow for multiple solutions. So if you have a multi-well energy, a non-convex energy, then you allow for multiple solutions. And when you look to the nature, this is quite natural that energy-based models should allow for multiple solutions. For example, consider a soap film. When you play around with soap films, then depending on how you move a wireframe to span the soap film, it can end up in different locally optimal solutions. So this is something that comes from nature. Another nice feature of energy-based models is that the solutions can usually be characterized based optimality conditions. For example, the famous Mumford-Schaaf functional for computing piecewise smooth approximations to functions. Is a very nice example of how you can characterize the local geometry of solutions. Then energies also provide a quality measure for a particular candidate. If the energy is high, then this is a bad candidate for a solution X. And if the energy is low, then it's usually a better candidate. Of course, if your energy is modeled nicely. And sometimes you can even connect the energy with some physically meaningful term, like a mean squared error, PSNR, or whatever. Then there's also a direct link to statistical modeling and Bayesian inference by simply plugging the energy into a Gibbs distribution. So you can say that the posterior P of X given the input Y is proportional to exponential of minus your energy of the configuration between X and Y. And based on that relationship, you can also consider stochastic differential equations like Langevin dynamics, and you can start generating samples from your posterior by driving this Langevin dynamics on your energy. And the stationary solution of the Langevin dynamics is then the complete posterior distribution. And of course, most interesting for us, if you don't want to that every problem is replaced with a feed-forward network, optimization-based models or energy-based models keep us optimization researchers busy. So what about energy-based models in computer vision, machine learning? In computer vision, in the last 20 years or so, you have mainly seen two different approaches: discrete optimization methods based, or they're defined through a maximum a posteriori inference of Markov random fields. They're usually called MRFs or ZeroFs in computer vision. Or the continuous counterpart are variational models. I already mentioned the famous segmentation model of Mumford and Schaaf. There are also different hybrid forms that combine discrete labels with spatially continuous models, for example, for computing minimal partitions. Then in machine learning, energy-based models have been used for many years, and they have a long tradition dating back to Hinton and Lacan, as you can see, but also more recently as an alternative to generative adversarial networks, for example, the paper by June Mortach. But also in discriminative learning with a Wasserstein-GAN, the discriminator can also be seen as some sort of energy-based model. And there's also an interesting paper by Graphical quite recently. They show that any deep learning-based classifier that has in the end a softmax classifier can be related to energy-based models and opens up generative learning. So how can energy-based models be trained? Assume that we're given a set of ground truth output and input pairs, xn and yn are the inputs, and xn are the matching ground truth solutions. And we consider an energy that is parameterized by some parameter vector theta, no matter what theta represents, just a handful of parameters. So one of the earliest approach for learning with energy-based models is due to Hinton. We try to find the parameters theta of the energy such that the energy should have low values on ground truth pairs, and it should have higher values on contrastive pairs, where we perform a wrong match between the input yn and the wrong output x tilde. And then there are different choices how you can produce these wrong matches x tilde. For example, you can do this by means of a generative adversarial network, where you end up with a min-max game, where you try to find a bad x tilde. Or if you just consider plain maximum likelihood learning, you can actually see that the contrastive term here is given by the soft mean of all possible choices xn. So it's a kind of a partition function that goes into the contrastive term. But also later we will see that we can use different contrastive terms that tries to find solutions x tilde that have a low energy, but that are sufficiently far away from the ground truth solutions xn. Then clearly bi-level optimization. So this is the most optimization-based approach. We try to find the parameter vector theta such that the solutions x and hat, which are the minimizers of our energy-based models for a given input yn, minimize a certain loss function. And With this, we get a bi-level optimization problem, where the higher level problem is the loss function that matches the outputs of the energy-based models with the ground truth solutions, and the lower level problem is just a solution of the energy-based model. And something that works very well in practice is some sort of truncated optimization. Here, what you're doing is, instead of using the true minimizer of your energy-based model, you replace it by the kth iterate of some iterative algorithm that minimizes your energy-based model. For example, if your energy is smooth, then you can just unroll some steps of a gradient descent algorithms, but later we will see that we actually can do this also with different algorithms. Something that is also interesting with unrolling is that if you consider this unrolled algorithm, this already looks very similar to a feed-forward network. So this provides a direct link between optimization-based methods and feed-forward networks. And also recently, there are technologies for so-called black box differentiation. So people found out that, for example, if you need a shortest path algorithm or graph matching algorithm within a convolutional neural network, you can learn that from scratch, but it doesn't generalize very well. So therefore, they considered implementing, for example, Dijkstra's shortest path within a neural network. And for learning of the neural network, you of course need to differentiate through this Dijkstra shortest path. And this is what they call black box differentiation. And they have designed different algorithms that give you relaxed solutions of the derivatives of black box solvers. And the good thing about these black box solvers is that you don't need to know what's happening inside the box. You just need to be able to call the minimization algorithm of your black box. But so far, this is restricted to linear objective functions. So now let's move forward to a particular class of energy-based models, which I will consider in more detail. So they are settled in computer vision and in more particular in image labeling. Image labeling is a task where you want to solve a certain image processing or computer vision problem, where you have given a set of labels. Labels could be gray values, could be color values, or labels could be depth values here in this case, or this could be motion vectors, or they could also be semantic labels in case of image segmentation. And you set up an energy such that your desired solution to the minimum of the energy performs an optimal labeling of your image. So usually this is described by means of a graph that has nodes and edges. The nodes correspond to image pixels. And as you see from these small boxes here, every image pixel can take 1 out of 3 different labels here in this example. And there are also connections between different labels of neighboring image pixels. And that are the edges, which somehow encode the neighborhood system or the neighborhood relations. And once we have set up your energy, this can be done handcrafted, or later we will do it by means of learning. Actually, you try to find that configuration that minimizes your energy, and this should solve your computer vision or image processing task as good as possible. So the energy which we consider here is a very standard energy, which consists of so-called unary and pairwise terms. So we can attach energies to choices of labels per pixel. So these are the unary terms. So for every pixel, selecting a different label in that pixel has a certain energy value. This is encoded with theta I. But there are also costs for pairwise labels. For example, here I have selected label 1, and on the next pixel I have selected label 2, and there's a certain cost for this choice. For example, we can take the absolute differences of the labels. So here, from here to here, this would be cost 1, and from here to here, this would be cost 2. But sometimes, you know, if you have semantic labels like tomatoes, apples, then there are completely different costs for the pairwise choice of labels. So what you can also see here is when we just crop out one line of an image grid, so that we have just a chain, minimizing this energy just amounts for solving a shortest path problem. So we just want to get from the left-hand side to the right-hand side and select a path that has the shortest or the smallest cost. And this also suggests that for these chain-like problems, or more general tree-like problems, there will be very efficient algorithms for minimizing the energy. Namely, it's exactly a variant of the express shortest time. But this I will explain later. So here's the relation from this discrete energy then to Markov random fields. As I have already mentioned, a nice feature of energy-based models is that they can be interpreted as the negative log posterior distribution, or the other way around. The posterior is given as one over some partition function z times the exponential of minus the energy divided by some parameter t, which in physics is called the temperature parameter, but it's basically some sort of variance. And there are two popular methods for performing inference on such Markov random fields. One is the so-called maximum a posteriori inference. It's called maximum a posteriori inference because you're trying to find that labeling of your problem that has the highest probability, the highest posterior value, and this is clearly equivalent to minimizing the energy. But you can also do a marginalization, so you can try to find the posterior just for the labels of one pixel, and for this you need to sum out, of course, all other labels of all other pixels. And this is a huge sum, and it turns out that for a particular structure of your problem, you can do this efficiently, as efficient as you can perform the minimization task. So I just wanted to show on the next slide what is the difference between marginalization and minimization. This is just for a 1D signal denoising problem. So given here in black a noisy signal. The same on the right-hand side, and on the left-hand side, we are performing marginalization, and the marginal probability is this shaded function you see in the background. And on the right-hand side, actually, we perform minimization. And you see the problems are related, the solutions to the problems are related, but they are not equivalent. For example, for the total variation, which was used here as a regularization term, the well-known staircasing artifact appears. So, which means that the signal is approximated with piecewise constant solutions. It's a well-known problem of the total variation. But if we perform marginalization, actually, we see that this does not appear, so get more natural results. Something that is very interesting is when you consider the algorithms for solving the left-hand side and the right-hand side, marginalization versus minimization. It is just the replacement of the minimization operation with a smooth minimization operation, which is the log sum x function. So it's in particular negative of log sum of the negative. So it's the negative of the softmax function. But it's exactly the same algorithm, just minimization and log sum x operation. So now let's move forward towards algorithms that can not only minimize the problems on a chain, but that can also solve the complete problem on grids. But first we need to reformulate it. First of all, the image labeling problem will be recast as a binary optimization problem. So this is something that is sometimes called lifting. For example, it has also been done in the continuous domain by Alberti, Buscite, and Dalmaso to get a convex representation of the Mumford-Shah functional. And with this approach, they have been able to prove that certain solutions are really global solutions of the Mumford-Shah functional by means of a so-called calibration approach. So here the basic idea, and also the idea of this calibration approach of Mumford-Shah, is that you replace your original optimization problem, which in our case here is a combinatorial with labels, as a binary optimization problem. So you replace labels yi, which could be tomatoes, apples, or just numbers, to binary indicator vectors, or sometimes they're also called one-hot encoding vectors. For example, if you have 5 labels and the label yi is 3, then the corresponding one-hot encoding is a vector 0, 0, and on the third position it has a 1 and the rest is 0. So with this, we can equivalently reformulate our optimization problem with this energy here. So you see now it's here a linear objective between the parameter vector and this binary vector. And here it is an outer product between 2 binary vectors of neighboring pixels. And you have to multiply it with the matrix that encodes the cost, and you consider the trace. So then the natural next thing in order to make this problem convex, because the previous problem was still non-convex, because we're optimizing over binary vectors, is you replace binary variables xi by vi that live in the unit simplex, and you replace these outer products of xi and xj with variables wij that also live in the unit simplex. And then in order to make the problem as well as good as possible connected to the previous problem, we need to introduce certain constraints. For example, that this is a unit simplex, so vi lives in the unit simplex, and also these marginalization constraints. If you sum up this wij on the matrix in one direction, it must give vj, and in the other direction, it must give vi, and also wij must be greater or equal than 0. So something here, what you can notice, if wij is greater or equal than 0, then of course these first constraints are redundant here. So this is a very famous relaxation of this Markov random field, and it is also known as the marginal polytope relaxation, and it dates back to Schlesinger of 1976. So people, for example, analyzed the integrality gap guarantees you get for this relaxation, for example, the paper of Jekuri. So where you can check if you solve the relaxation, what is the worst case in terms of a function gap related to the original binary optimization problem. So when you recast this as a linear program in standard form, you get a huge linear program with n squared times k squared variables. In image processing, n is usually 1000. So you see n squared is 1024 squared, and 256 labels is standard in computer vision. Then you have 7 times 10 to the 10 different variables you need to solve. And this is, of course, a huge problem, and usually this cannot be solved by off-the-shelf LP solver. However, there's an important observation. The dual problem is usually much smaller. It only has 3 times 10 to the 8 variables, because the dual problem basically is defined on the number of constraints. So I would like to mention a few state-of-the-art algorithms that can solve these Markov random fields. I already mentioned that the standard marginal polytope relaxation using off-the-shelf solvers is slow, and usually this is restricted to small problems, doesn't work for practical problems. But there's one very nice algorithm that is exact on trees, for example, chains. It is a max product belief propagation, dates back to Pearl of 1988. And this is basically just a variant of Dijkstra's shortest path. However, for graph with loops, and I will comment on that later, it still can be used. There's a heuristic, but it may not converge, and you can easily construct examples where it actually diverges. So around 2000, this was the age of graph cut algorithms. There were move-making algorithms that reduced the overall optimization problem to a sequence of binary optimization problems, and every binary optimization problem has then been solved by means of a graph cut for which very efficient algorithms were available. This works very well for certain problems, but in case you have many labels, actually this algorithm slows down. Then the next algorithm that really was the next level of performance for solving such problems is the tree-related message passing algorithm due to Wainwright, Yakula, and Wilsky. It is basically a decomposition of the original problem into trees, and on all the trees you can apply belief propagation exactly, and then the results of the subroutines solved by belief propagation is then combined, for example, average. This algorithm, again, works very well in practice, but also has problems with convergence guarantees. And that was the next level, and this is an algorithm due to Vladimir Kolmogorov. It's a sequential variant of TRW, tree-related message passing, and this was shown to give a monotonous coordinate ascent on the dual, and basically you can show that it's a coordinate ascent on the dual problem, and it monotonously increases the dual objective, but of course it's coordinate ascent on a non-smooth problem, and therefore it might get stuck in an optimal point. Then there are also different smoothing approaches in line of Nesterov's smoothing. Basically, you consider a dual problem, and then you replace the minimum operation again with some log sum x operation, And for this, you can then efficiently compute derivatives, and then you can make use of accelerated gradient algorithms in order to minimize this smooth dual objective function. There's also one algorithm that is a sort of a parallel, highly parallel variant of TRWS, which we developed some years ago together with Alexander Shekovtsov, which also works very well in practice and which I will explain a little bit later. Very recently, together with Vladimir Kolmogorov, we considered the subtle point formulation, which is again, it comes from a Lagrangian relaxation of the problem. I will give details later. And we have shown that actually there are proximal maps which you need to compute, and you can make use of linearly convergent Frank-Wolf algorithms. And when you do so, then you get a fast converging algorithm that can solve exactly the relaxation with non-convergence rate. So before I come to the algorithms DMM and the one-sided saddle point Frank-Wolf algorithm, I just want to mention how you can exactly solve this problem when you restrict it to a chain. So let us restrict the image shaping problem just to one line, and we assume that the line has n nodes from 1 to n. We give them labels from 1 to n, and the nodes represent image pixels just in one line of the image. Then clearly the edge set is given by pairs of neighboring nodes along that line. So the edge set is given by 1 and 2, 2 and 3, 3 and 4, and so on. As before, every node I can take a label out of a given label set Y to be defined. And the energy we would like to minimize is we minimize the unary terms along the nodes from 1 to n, and we minimize the sum of the pairwise terms between pairs of labels along the line. So now here is the main observation why this problem actually can be solved efficiently. So when we write down again this energy, this here, then actually we see that we just put together the first unary term and the first pairwise term. So we have theta1 of y1 plus beta1, 2 of y1 and y2. Actually, we can just sort out the minimization with respect to y1 for these two terms and give the resulting function the name f2 of y2. So if you minimize out y1, we have a resulting function f2 that just depends on y2. And it turns out you can compute this function f2 just by trying out all different pairs of labels. And then you do again, you define the function f3 of y3, where you have now this f2 from the previous line here, and you have the second unaries and the second pairwise term. And you do so until you reach the end of your chain, then actually you end up with minimizing just the function fn of yn plus theta n of yn. And if you have successfully computed all this function f2, f3, f4 up to fn, which is possible, you just need to enumerate all these different y's, select that one with the minimal energy, and then you have found your minimum energy, and you can back propagate the solution to the beginning. As you can see, this is nothing else than Dijkstra's shortest path, just specialized on this particular problem. So here is it, it's written down a little bit more formally. We start with these functions f1 to be 0, and every other function fi of s is then defined by minimizing the previous function fi minus 1 of t plus these unary terms plus these pairwise terms. And for every different choice of s, you need to minimize with respect to t. So this also means that if we have, for example, k labels, the complexity is k squared for solving this optimization problem. But for example, if you have more structure in your pairwise terms, like the total variation, it turns out that you can speed up the computation, and it's also linear. It's only linear in the number of labels. So because this then represents a minimal convolution. So these functions which we have computed here, they are in the literature called the Bellman functions, or in this context of belief propagation, they are called forward messages. When we do the other way around, we don't go from left to right, but we go from right to left. You can do exactly the same. So you start on the right-hand side, you initialize your backward messages with 0, and you compute the other messages again with the this recursion, then you end up with the backward Bellman functions or backward messages. Once we have computed the forward and the backward messages, it turns out that we can compute a quantity which is called the min-marginals. The min-marginals are defined as you are considering a certain node somewhere in the middle of your chain, and you fix the node to a certain label, and you minimize out from left and right all other labels. And the value of this energy for a particular node, for a particular label in that node, is the so-called min-marginal. So you must consider you take a node, you fix a label, and you force your solution to pass through the label. What is the value of the best or the smallest energy that passes through this certain label in that node? And it turns out that you can efficiently compute the min-marginals by simply computing the forward messages, the backward messages, and you add together the forward and the backward messages plus the unaries in this particular node. And with that, you exactly get the min-marginals. And once you have computed the min-marginals, you can just select in every node the optimal label. So then there is no need for computing forward messages and doing a backtracking. You do it forward, backward, add together, and you select the optimal label. So what about an extension to grid-like graphs? Unfortunately, this dynamic programming, this just works on chains, or more general on trees. For here you have represented a tree that spans a pixel grid, or is the largest, one of the largest trees you can put to a pixel grid. You can, for example, compute the min-marginals exactly in this point by propagating all these messages to this node. And it turns out that if you start to alternate these trees horizontally and vertically, so these two different choices of trees you can generate, and you start to reuse messages that usually exist here, but which are not drawn here, because otherwise it would not be a tree, then you obtain a very efficient variant of loopy belief propagation, the so-called sweep belief propagation algorithm. And it turns out that this algorithm works very well in practice. So it gives very fast and very nice solutions, usually after 5 or 10 iterations. But unfortunately, it doesn't give any guarantees for convergence. It could even diverge. So here's the more formal description of the algorithm. First, you have horizontal and vertical message for both forward and backward. You initialize all of them with 0. Then you define auxiliary unaries, where you add to your unary terms the other forward and backward messages, and then you solve for the horizontal. And then you alternate. You define auxiliary unaries, where you add just those previously computed horizontal messages to the unaries, and then you solve for the vertical. And if you start alternating this, you get this very fast algorithm. And there exist several variants where people try to fix this theoretical shortcoming of belief propagation. One of those message passing algorithms is, for example, TOWS, that works very well in practice. So now let us turn to a more optimization-based perspective of this problem. Namely, we make use of a Lagrangian decomposition of our problem. So based on the structure that when we have a pixel grid, we can solve all horizontal chains and all vertical chains optimally. We just cannot solve the sum of the two. We can consider the following splitting. We say that we minimize the sum of the two energies, but now with two different variables, y1 and y2, with the constraint that y1 equals y2. So this is the standard Lagrangian decomposition tree. And then what you're doing, you're introducing a vector of Lagrange multipliers that actually takes care of the difference between y1 and y2. And since this term here is just defined on the unaries, so there's one lambda for every pixel, for every node in our graph. Actually, you can easily solve the horizontal chains together with lambda times y1, or you can easily solve E2 together with lambda times y2. And when you minimize out with respect to y1 and y2, you get clearly the dual problem. And it turns out when you wonder which problem you are solving now with a dual problem, of course, this is a relaxation, so it's below the original problem. But when you start to play around a little bit with conjugate functions, biconjugate functions, and informal convolutions, you easily see is that you are trying to minimize the sum of the biconjugates of the single problems. And this is clearly below the original problem. And it also has been shown in different works that this Lagrangian relaxation is actually equivalent to the marginal polytope relaxation. But now it has a structure that opens more possibilities for fast optimization algorithms. So that is an algorithm actually that makes use of this Lagrangian decomposition, which we have developed some years ago together with Alexander Tchekhovtsov. It is a so-called dual minorize-maximize algorithm. So it's basically the same when you do majorize-minimize, but since we are solving the dual problem, we need to minorize the dual problem from below and then maximize the minorand. The basic idea is that when I go back here, we have here in the dual problem actually two dual functions. So it is E1 star of minus lambda and E2 star of lambda. And the algorithm proceeds as follows. You fix one of the dual functions to be the original function, but the other function actually is replaced by a minorand. And the minorand should be constructed in a way so that we can solve this maximization problem of the minorand plus the second original function easily. And this is actually the case when this minorand just consists of unary terms. And the algorithm we have proposed on a more general level works as follows. You consider your first dual function and you try to remove as much as unary terms from this problem without changing its minimizer. So you're trying to subtract unaries that still preserve the minimizer of the first problem. And once you've done this, you take those unaries and add it to the second function, because the second function, which is still original, can still be solved together with the unaries removed from the first time. And of course, you have to make sure that actually it must be a valid minorand, so that in the iterate lambda k, the value here is equivalent to the original problem, and that overall it's a minorand to your problem. And clearly, this algorithm yields a monotonically increasing sequence of dual function values. And another good thing is that we can compute those minorands, and they are in fact maximal modular minorands. So there are no larger minorands by means of a hierarchically dynamic programming approach. And this, in addition, can be efficiently implemented on the GPU and gives an algorithm that even works in real time for relatively large problems. However, there's still one problem. What we're doing is a block coordinate ascent on the non-smooth dual. So it could be the case that the algorithm might get stuck in non-optimal points. So this is more or less a motivation for the development of algorithms that are relatively fast, but can solve the relaxation exactly. So let us consider here a more general discrete optimization problem. And the previous problem of the Markov random field is just a particular instance of that. So we are minimizing a sum of functions ft, and the function ft is restricted to just a subset of variables of our variable vector x, and x is a binary vector. Okay, so and t are called the terms, for example, and at is the number of, or is the set of variables corresponding to this particular t here. When I relate this to our previous problem, we just had two functions. ft, one is for the horizontal chains and one is for the vertical chains, and actually depending on which chain you are considering, this x is restricted to the pixels appearing in the particular chain. So what we assume, and this is the most important assumption here, that we have an efficient linear minimization oracle which I call LMO, that can solve for a given vector y this problem here for a particular t efficiently. So it can efficiently minimize this binary optimization problem of this function ft plus this linear term here. And again, to relate this with our previous problem, this is exactly dynamic programming on chains where we can add different unaries. It does not make our problem more complicated. We can still solve it if we add something to the unaries. So now this problem can be equivalently written as an optimization problem over polytopes. So for this, we define the polytope T as the convex hull of X, which are these binary variables, together with an additional coordinate that represents the function value f of x. And so it's in r to the at. This is the set of variables for this particular term t times r, and this additional dimension is for the function value. And we also denote as this x naught t as the last component of the vector xt. And this last component corresponds to the function value in this polytope. And then we can rewrite this optimization problem as minimizing the sum over t of this x naught t, because they are the function values. And we have the constraint that xv must be equal to xvt for all t, and v restricted to the set of variables corresponding to the term t. So it's again the same splitting as we had before, but here it's written in just a more abstract way. And this problem is still non-convex because here we have again this integrality constraint that x is restricted to binary values. And then usually after dropping this constraint, we can rewrite this problem as a convex concave saddle point problem where we minimize with respect to all these x's in these polytopes, convex polytopes, and we maximize with respect to y, which are the Lagrange multipliers. And additionally, these Lagrange multipliers we've introduced here, they must satisfy that their average is 0. Okay, so this previous problem is again just an instance of a more abstract saddle point problem of the following form. So you have this bilinear term here, kx times y, plus a function fp of x minus h star of y. So we have a particular structure which we assume and which we would like to exploit when we have an algorithm for solving the saddle point problem. First of all, the function fp is the sum of a function f of x that has a Lipschitz continuous gradient, plus the indicator function of a convex polytope, delta p of x. And as I have mentioned before, we assume the existence of a linear minimization oracle that actually can efficiently solve this problem here. So minimizing of this linear function over this convex polytope. And the second assumption which we're having is that the function h star is a convex function, and we assume that we can efficiently compute its proximal map. So this is usually, for example, if h star is some convex set that we can efficiently compute the projection, or if it's a L1 norm, we know that there's the shrinkage function and so on. We also call f of x the primal problem when we maximize over y, because we must assume that this exists, and h of y is the dual problem when we minimize over x. And we assume that strong duality, of course. So the first algorithm that needs a little bit more structure is an accelerated dual proximal point algorithm. In fact, it's a sort of a Primal-dual algorithm, but you can write it down solely just on the dual problem. And in order to make this algorithm work, we need to assume that f of x, remember this is this function with Lipschitz continuous gradient, is a quadratic function, and the convex function h star, for which we need to compute the proximal map, must be a linear constraint. And if this holds, actually it turns out that we can just perform a proximal regularization of the dual with respect to some parameter gamma and the given point y bar. And for this regularized saddle point problem, just on the regularized on the dual, we can again compute a primal problem, and we can compute a dual problem. And now if we consider just a proximal point algorithm on the dual problem, just on h gamma y bar of y, it turns out that still an intermediate primal variable is needed, and therefore you can again write it down as a sort of primal-dual algorithm. In this primal-dual algorithm, actually what you need to minimize is the primal-dual gap between f gamma y bar of x and h gamma and y bar of y. And since we assume that f is a quadratic function and h star is a linear constraint, it turns out that this primal function here is still a quadratic function because it's the Moreau envelope of a quadratic function. And in this primal function, we need to minimize a quadratic function over a polytope, because also the function fp goes into the definition of this primal problem. And it turns out that there's a class of linearly convergent Frank-Wolf algorithms, for example, Frank-Wolf algorithm with the wave depth, or the blended conditional gradient method, or the decomposition invariant conditional gradient method, that enjoy a linear convergence rate on such problems. For example, I would also like to highlight the method of Beck and Stern. This gives a linear convergence rate even if the objective function is not strongly convex. You just need that it's a composition of a strongly convex function with a linear operator plus a linear term. And this is exactly what actually we have then to solve in our problem. So we can assume that we actually can compute approximate solutions to these iterations of a proximal point algorithm where the convergence is linear. And this gives us the possibility to apply an inexact accelerated proximal point algorithm on the dual. And here we make use of the algorithm of Ojol and Dosal. And this algorithm still has a 1/n squared convergence rate on the dual problem, still if we have some inaccuracy of solving the iterates. And actually what we are doing, we are prescribing the accuracy in which we need to solve these proximal subproblems. And if the accuracy goes down to 0, or vanishes to 0 with high enough rate, actually we can show that we get a 1/n squared convergence rate. So what we assume is that the function minus h of y is coercive. And we also assume that the subproblems in X are solved with a linear convergent Frank-Wolf method, one of the many variants. And then we can show that the inexact accelerated proximal point algorithm makes n log n calls of LMO, for example, dynamic programming, in case of Markov random fields during the first n iterations, and the dual iterations satisfy then this 1/n squared convergence rate. And here this iterate y and e is just an ergodic combination of previous iterates. So it turns out that with this algorithm, we can indeed solve the marginal polytope relaxation of the Markov random field exactly with guaranteed convergence rate. But on the downside, I need to mention that it is still not as fast as the good old belief propagation or the DMM algorithm I have mentioned. We have also considered a more general class of inexact primal-dual algorithms, actually where the functions f and h can be more general, so they're not restricted to quadratic functions and linear constraints. In this case, we can still apply the inexact primal-dual algorithm of Julian Rasch and Antonin Chambol, and the proximal subproblems that appear in these inexact primal-dual algorithms are solved up to accuracy epsilon, again with linearly convergent Frank-Wolf algorithms. And for this algorithm, we have also shown that the inexact primal-dual algorithm makes order n log n calls to the linear minimization oracle during the first n iterations, and the dual iterations then enjoy a 1/n convergence rate. In addition, if we make sure that the domain of H star is a compact set, for example, by just knowing that the duals are bounded, then the primary iterates also enjoy the same convergence rate. So here, just some results out of the paper where we compared the accelerated proximal point algorithm with the non-accelerated proximal point algorithm that has already existed in a paper of Vladimir. And this is one instance of image denoising where the energy is very similar to the Mumford-Shah function. So it's a piecewise quadratic potential function in the pairwise terms, and this is a simple stereo problem. And as you can see, the solid lines correspond to the accelerated proximal point algorithm, and they give a better performance on these problems. And depending on the accuracy alpha, we prescribe for solving the proximal subproblems, the iterations are faster in the beginning, or here if we need take alpha equals to 4, then okay, we did not run it to the end, but you can assume that in the end it will catch up the previous lines. So finally, I would like to mention something about learning. So because this was also part of my talk, and this is also a reason why I'm very much interested in having fast solvers for Markov random fields and conditional random fields. So for decades, the unary and pairwise terms, they have just been computed based on handcrafted features. For example, there were normalized cross correlations in stereo for feature matching, or there were piecewise quadratic or piecewise linear potential functions for the pairwise terms. But now, of course, in the age of deep learning, it is quite natural to replace those handcrafted factors that go as an input into your Markov random field and to replace it by learned features. And there are several works we considered where we had a unary convolutional neural network that computed the terms, the unary terms from the input images, and also the pairwise terms were computed from the input images. And they go as input into the Markov random field, and then the final result is given by minimizing the Markov random field based on those energy terms computed from the CNNs. So basically, we had 2 papers at CVPR where we suggested different methods for learning together with Markov random fields, because still, you know, you have your convolutional neural networks that have many parameters, and the output of the neural network goes as input into your energy-based model, and the final solution is then given by minimizing your energy-based model. And for learning, you need to back propagate the error of your loss function that compares your output with ground truth solutions through your minimization model to the parameters of a neural net. So the first approach is the following. First, we consider the bi-level optimization problem. We try to find that parameter speeder of our neural network such that the minimizers of the energy-based model minimizes a certain loss function. But for combinatorial models, this is bad because it's non-differentiable. And therefore, we need to get some approximate solution or some approximate formulation of this bi-level optimization problem. And one such approximate solution comes through the so-called margin rescaling technique, which is closely related to the support vector machine. This model is also called the structured output support vector machine. And basically, what you're doing is you consider an upper bound to this bi-level optimization problem. And the first thing you're saying is that, okay, I would like to maximize my loss function, but X should still be a minimizer of my energy-based model. Okay, so in case X is non-unique, you will select that X from a set of minimizers such that your loss function is for fixed beta is maximized. Then you say this is less equal when I make this, I relax this slightly and say, okay, I'm not interested in minimizers, but at least in solutions X whose energy is smaller than the energy of the ground truth solution, because we should assume that the energy of the ground truth solution should also be small. Okay, this is the first relaxation. The next relaxation is that you say, okay, the left-hand side of this inequality is smaller than the right-hand side, so I can add the difference, still makes the right-hand side larger, and then the next step is you simply drop this constraint. And then what you get out is something very natural. It's namely a contrastive learning approach, which I mentioned in the very beginning. you would like to learn the parameters beta such that the energy is small on ground truth output input pairs. But you would also like to identify through an auxiliary minimization problem samples X that have a low energy, but are far away with respect to the loss function of the ground truth solution XM. So these are the particular contrastive examples which have a low energy, but that are not too close to the ground truth solutions. And as you can see, in order to identify this example X here that has this contrastive property, we need to call the MRF solver as a black box. And for this, we need, of course, an efficient solver. And the only difference is that we need to add those negative loss functions to the unaries. So here's a graphical explanation. Actually, this is the loss function here. I used a truncated linear loss function. And at the ground truth solution, which is this blue dot here, of course, this term is 0, but then it increases like a truncated linear function. And actually, this is the example which we have identified when we added this blue function to the usual unaries. And this difference here indicates that this prediction is below the margin. And therefore, when you take the derivative of this formulation, once you have identified X, you will get a gradient that pulls down the energy on the ground truth examples and pulls up the energy on this contrastive example. So it pulls down the energy here for the ground truth label and pulls up the energy for this contrastive example. And I would also like to mention a second mention, which is more recent, again, a CVPR 2020 paper. And here we did not treat the MRF solver as a black box, but we treated it as a white box. So we used an algorithm that can minimize the Markov-random field. In this case, we used just the belief propagation because it was so efficient in practice. And we computed from the min-marginals, if you remember, I have explained on the previous slides, and from the min-marginals, which can be interpreted as approximate true marginals of your statistical model, we normalized those marginals, and then we used them in order to set up a loss function that minimizes the cross entropy between the normalized min-marginals and the distribution given by the ground truth solution. And what we basically did is we unrolled a certain number of iterations of our belief propagation algorithm, and then it turned out that computing a derivative backwards from the loss function through the unrolled belief propagation iterations to the parameters of the unary and pairwise CNN can be done efficiently, again using dynamic programming. So finally, I just show some results. And once you have learned the model, it works very well for stereo computation. These are some examples for the so-called cityscapes database, which is used for evaluation of models for autonomous driving. And you see one of the input images of a stereo pair. And here you see a color coding of the depth image computed by the Markov-random field. And since we have such an efficient solver that can be also parallelized on the GPU, computing the solution works in real time. On the right-hand side, this is a similar work, but now this is still a more complicated problem where we had a Markov-random field for motion estimation, or it's also called optical flow. Here the color coding of the label indicates the direction and the velocity of the motion. So every different hue is a different direction of the motion, and the saturation tells you the speed of the motion. So, and you see it works very well. And here the number of labels are several thousand labels. Okay, this already brings me to the conclusion and the discussions. I was talking about energy or equivalent optimization-based models with applications in computer vision. And I've shown that fast solvers are important for both inference, for example, to apply a model in real-time processing, but also during learning, because, for example, with the surrogate objective function, in order to identify the contrastive examples, you need to have a fast solver in order to compute derivatives. And I've noted there's still a remarkable performance gap between fast heuristical methods, such as belief propagation or the dual minorize-maximize method, and methods with guaranteed convergence rate. So the saddle point formulation I was talking about is guaranteed to find a solution of the relaxed problem, and it also comes along with a guaranteed convergence rate, but still in practice, it's, I would say, one order of magnitude slower compared to the heuristic methods. And also discuss different methods for learning that can deal with the combinatorial nature of these Markov random fields. One was for black box learning, where I computed an upper bound based on marginal rescaling, and the other one was unrolling iterations of an algorithm that computes a proximate solution of a Markov random. So with this, I would like to thank you for your attention, and I'm looking forward to your questions. Thank you very much.
Thank you very much for a very interesting talk. Very nice applications. So, are there any questions? Yes, Jonathan. Or let's start with Heng Yang. What's first?
Yeah, can you hear me?
Yes.
Okay.
Yes.
Yeah, so I have a thanks for the very nice talk. So I have a question for the final part about the bi-level programming. So I was wondering, since the lower level problem is a non-convex problem, I remember that from one of the last lectures about bi-level programming, they say that if the lower level programming is non-convex, then if you try to derive the gradients using the KKT conditions, somehow they say that the KKT conditions are not sufficient to even guarantee a local minima of the original bi-level programming. So
that's completely right. So this is the reason why we did not solve the original bi-level problem here. So we constructed an upper bound, the surrogate.
Okay. So and then so I wonder if if for some reason suppose I have a bi-level programming and the lower level programming is non-convex.
Yes.
But for example, I have a semi-definite programming relaxation that can solve the low level programming exactly. Does that help in terms of solving the original bi-level programming? So if I...
It's a good question. I have to admit I don't know. So I don't know. I mean, then of course your lower level problem is convex. Okay. When you say I'm just interested in solving the relaxation, then it's convex. And what are the conditions that guarantee that you solve your original problem? That's a good question. I don't know, but it's very interesting, I guess.
Okay. Okay. So okay, good to know. Thank you.
Thank you, Jonathan. So we can't hear you. Okay, probably now. No. There is some noise. Okay, then Tom. So in the discrete model, after constructing this convex hull in, let's say, dimension n+1, yes, it was the vector and then the function value.
Yes, exactly.
Then you kind of drop the 0-1 condition.
Yes.
Okay, is this a big loss?
It's actually exactly the same relaxation as before. So it's always the same marginal polytope relaxation you obtain. So it's you can solve the sub problems on trees or chains exactly binary, but once you need to solve them together, you of course, in order to get a convex problem, you need to drop this constraint. And in the end, what you're solving is, as I said, it's the sum of the two biconjugates.
Okay. Yeah.
Or here in this example, it would be the sum of the biconjugates of the single functions in the more general problem.
Okay.
But I think it's the best we have so far.
Yeah, it's clear. Yeah. So Jonathan is writing in the chat. So he's asking if there is a case in which there is a benefit to find the actual integer solution rather than the relaxation. So if
I mean, I think for image labeling, no.
Okay.
I don't think so, but you know, this there are different problems like protein folding, which enter exactly the same structure and which are usually much harder to solve than image labeling. I think then it's in the end you must round your solution.
Yes.
And then in rounding you must make sure that all your constraints are satisfied. For example, I guess it could be a problem.
Indeed. So then you want to stay integer at the end to go back to some integer solution.
Yes.
Yeah. This makes sense. Yeah. So are there other questions? Then I have a question on this Primal-dual approach.
Yeah.
So this is kind of interesting, since usually this improved rates, they are related with the strong convexity, which is here not given, I guess.
Yes.
Yeah. Okay. This is another.
You know that the subtle point is that you have for the composition of a strongly convex function a linear operator, which must together must not be strongly convex linear convergence when you use Frankfurt.
Yes.
For example, I tried hard to understand how you can get this 1/n squared with a primal-dual approach. I don't know how. I don't see where the strong convexity comes from. So this is
yeah. It's clear.
No, at least I don't see it.
Yes.
Maybe for somebody from the audience, it's obvious I don't see it.
Great. So, are there other questions? So no other questions, Tom, then let us stop here. Thank you very much for a very nice talk.
Thank you very much for the invitation.
Very good discussion. So please send us your slides. We will post the slides in the video on the website of our seminar. I just want to announce that the last talk of the third season will be given next Monday by Heinz Bauschke next Monday. And then we'll have a summer break.
Great.
Have a great week. Thank you. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.